In this video, we're going to address the question, what is a capacitor? I would like to ask you to take a few moments to look at worksheet exercises number 1 for the capacitive elements and see the examples that are stated for the different types of capacitors. From looking at that example, we can see that we can define a capacitor as being any type of device that stores potential energy. And there are many types of devices from electrical, mechanical, hydraulic, and thermal realms, as well as many others that can be modeled as a capacitive element. So a capacitor is any type of element in any dynamic system that stores potential energy. In this class, we're going to be primarily concerned about electronic capacitors. So we're going to frame everything about capacitors in terms of electronics. So a simple model for a capacitor is that of two conductive parallel plates that are separated by an insulating material, where no current can flow through that dielectric or insulating material. Now, if we take the two neutrally charged plates and we place a potential source between the two of them, that is a power source, then we're going to do work on the charges between the plates and move charges from one plate to the other. We're going to move positive charges up towards this positive plate, and we're going to move electrons or negative charges to the negative plate, and in doing so we establish an electric field. Now, in theory, with an electronic capacitor, we could then remove that power source or that source of potential energy, and this electric field would remain indefinitely because there would be no way for the positive charges or the negative charges to recombine with each other. So when this voltage or this work is applied to separate the charges and create the electric field, this electric field will be retained indefinitely. What I want to say here is give a little note about the fact that this process of applying a potential across the neutral plates and coming up with a resulting electric field is often inappropriately called charging. The capacitor itself stores potential energy. It doesn't store any charge. And the way that we can look at that is we can see that this model of the capacitor right here has an initial neutral charge to it. By adding this work or applying a voltage or this potential difference that's developed, we're not doing anything to the capacitor, to the total charge across the capacitor. All we're doing is we're moving the charges around from one plate to the other. So the capacitor itself is not storing any charge. The only thing that we're doing is we're rearranging the charges so that potential energy is stored in the form of an electric field. Now, the reason this is called charging is because what happens when we do this is on one of these parallel plates we obtain a net positive or a net negative charge. So if we look at one of the plates of the capacitor in this model, we are actually adding or removing charge from that plate, but as for the capacitor as a whole, there's no net change in the total amount of charge, just the distribution of charges between the plates. Alright, now we can calculate or we can quantify how much capacitance is, or how much charge is stored on one of the parallel plates of the capacitor per amount of potential that's applied. And that is called capacitance, and it is measured in farads, which is equivalent to coulombs per volt. Alright, and it measures the excess charge stored on one plate of the capacitor per unit of potential difference across the capacitor. For these parallel plates, what we can do is we actually know that if we know the geometry of the system, we can fairly accurately calculate the capacitance if we have the configuration that looks like this, where we have two parallel plates separated by the dielectric material. So based on this geometry, the area of the parallel plates, the separation distance, and knowing the electrical permittivity of the material that separates the two plates, we could calculate the capacitance for this parallel plate capacitor model. However, most of the capacitors that we're going to work with in electronic systems do not have such a simple geometry to them. They're actually a bunch of plates that are folded over top of each other, and they have a very complicated geometry. So we're not really going to be concerned about how we calculate the capacitance based on geometry, but what the capacitance means and how we can use it and exploit it to our advantage in engineering situations. So a capacitor is represented on a schematic symbol by either this two parallel plates, harkening back to the parallel plate model, um, or by this symbol right here, which has sort of this curved parallel plate and a positive sign or a plus sign above one of the parallel plates. Now, in terms of analysis, these capacitor symbols mean exactly the same thing. They're both capacitors, and we're going to model them as ideal capacitors in our circuit schematics. It's important to note that the farad is a very large quantity of capacitance, and most of the capacitor values that we're going to encounter in common use are going to be in the range between picofarads and microfarads. So a farad is a very large quantity, so we're going to see actually pretty small quantities of capacitance. Now back to this non-polarized capacitor symbol and the polarized capacitor symbol. While they don't matter in terms of the analysis or in terms of how they operate or behave in theory, in practice it does matter because non-polarized capacitors are made out of different materials than polarized capacitors. And in general, polarized capacitors have a much greater range of capacitance. They can have a much larger value of capacitance to them. Now, non-polarized capacitors, it doesn't matter which way they go in the circuit. So either side, there's not a positive side or a negative side for the non-polarized capacitor. So they're typically small devices like the ones shown here, and they will they can be inserted into a circuit in either direction, and it's not going to matter. However, a polarized capacitor has a positive side or a high side denoted by this positive symbol right here, and a low side. So the low side always has to have a lower potential relative to the high side, and this is common in these types of capacitors that are shown in this bottom image right here. These are called aluminum electrolytic capacitors, and they actually have an electrolyte solution inside of them that provides a greater capacitance to these capacitive elements. However, because of this, we have to orient them a particular direction, and you can see here we have these arrows with these negative signs, and those negative signs and arrows point towards the low side lead of the polarized capacitor. Again, let me reiterate that in our analysis, it doesn't matter whether they're polarized or non-polarized capacitors. However, in actually implementing these devices, it is important to denote when we have a polarized capacitor which side has to be placed at the low potential side. All right, so a way I like the fluid analogy and for circuits, and I'm going to develop this fluid capacitor model to hopefully help us visualize a little bit better what the capacitor is doing. So in the closed system fluid analogy, we know that pressure is analogous to voltage and fluid flow or flow rate is analogous to current. So a capacitor acts like this fluid-filled sphere, and this sphere happens to be separated by this flexible membrane. Okay, so we have a hard sphere or hard tank, and then we have this rubber plate or bendable plate that's in between, in the middle of this. Okay, now if we imagine that we're going to increase the pressure on one side of the plate relative on one side of the tank relative to the other, or we're going to pump some fluid into this side, we see that we establish a pressure difference or a larger potential difference on one side relative to the other, and the membrane is going to bend. If we have an equal distribution of pressure, or analogous to no potential difference across the capacitor, this membrane is not going to flex. And if we have a pressure difference in the opposite direction, the membrane will flex the other direction. Okay, and that's analogous to a reverse voltage. Now, a capacitor doesn't allow a constant current to pass through it because it acts as an open circuit, and that's because the dielectric material of the capacitor doesn't allow a current to flow through it. However, and we can see that that's the case with our fluid capacitor model. If we put water or fluid in one side of this, it's not going to mix and it's not going to flow through to the other side. However, what I want you to do is imagine that if we didn't know that there was this membrane inside of this tank, and we started flowing water into this one side right here, and we started building pressure up. What's going to happen as this membrane starts to flex? Well, as this membrane starts to flex and we build up pressure on this side relative to the P2 side, what's going to happen is we're going to see some water or some fluid leaking out of this side of the pipe, of this side of the tank. Now, if we didn't know that there was a membrane there, it would look actually like there was some water flowing through the tank. But of course, we do know that this membrane is separating the two of them. All right, and that leads us to this concept of displacement current. So the capacitor does not allow a constant current to pass through it. It acts as an open circuit in this case. However, when the voltage changes or the pressure changes across this capacitor, it acts or behaves as though a current is flowing through the charges as charges are displaced from the conductive plates. Right? This is the same way that as we increase the pressure on one side of this tank, water is going to move out of the other side of the tank because it's being displaced because this membrane is moving or bending. Okay? So when the voltage or the pressure changes, it acts as though a current flows through it because charges or the liquid is displaced. All right, and we call this a displacement current. So if we increase the potential difference, as we are increasing the potential difference on the P1 side, or the pressure on the P1 side relative to the P2 side, it's going to look like there's liquid flowing out of the right-hand side of our tank here. And that would be the same or analogous to a displacement current moving through the capacitor in one direction. If we have a constant potential difference, there's no change, and so there's no fluid moving. It doesn't appear that there's a fluid moving through this tank. In the same way that if there's no potential difference across this capacitor, there's no current through the capacitor. And finally, if we decrease the potential difference, that is, there's a greater potential on the P2 side of this tank relative to P1 as we increase P2, or we increase the voltage on this side of the capacitor relative to the left side of the capacitor, there appears to be a displacement current moving through the capacitor from the right to the left. Okay, so even though current doesn't move through the capacitive element, it behaves as though it does when the pressure or the voltage across the capacitive element is changing. Okay, so from this we see that we have capacitor current and voltage relationships, just like we did with the resistive elements. For the resistive elements, we know that the voltage is proportional to the resistance times the current, V equals IR, or Ohm's law. We want to come up with similar relationships for the capacitor. So if you take a look at the exercises on the exercise 2 of the capacitor worksheet, we see that we can relate the current or the displacement current through the capacitor to the voltage or the change in voltage across the capacitor using this differential relationship. So this is similar to Ohm's law, except it's for a capacitor. We see that the current is proportional to the capacitance times the rate of change of the potential across the capacitor. Now this is a separable differential equation, and we can separate these variables and we can integrate, and we can also come up with a relationship for how the voltage across the capacitor changes depending upon the current through the capacitive element through integration. All right, and a couple of things we want to note here. Because the integration, that voltage is proportional to the integral of current, we see that voltage across the capacitor cannot change instantly. But the current, since it's proportional to the rate of change of voltage across the capacitor, the current through the capacitor, or the displacement current, can change instantly. So that's an important relationship to keep in mind. Okay, so because of this, capacitors introduce time dependence into circuits that contain them. All right, so when the voltage across a resistor changes, the current through the resistor changes instantaneously. But this is not the case with capacitors, because capacitors permit an instantaneous change in current through it, or an instantaneous change in the displacement current, but they do not permit an instantaneous change in voltage. Alright, so in steady state, no current flows through the capacitor and it acts like an open circuit. We can also use Kirchhoff's laws to determine the equivalent capacitance of capacitors in series. And we see that capacitors in series add together or combine together like resistors in parallel. So the equivalent capacitance is determined through the reciprocal relationship, or the reciprocal addition of all of the capacitors that are in series with each other. Similarly, we can come up with the relationship for adding capacitors or determining the equivalent capacitance for capacitive elements that are in parallel with each other. And we see that the equivalent capacitance is determined for parallel capacitors like it is for series resistors. That is, we simply add linearly the capacitances of all of the capacitors that are in parallel with each other. We can also determine the amount of power that's absorbed by a capacitor. It can be calculated by the product of current and voltage, but unlike a resistor, a capacitor does not dissipate any power. It only stores it. Okay, and this power can be retrieved at a later time by the system. Right, and using the current and voltage relationships, we can come up with these two different relationships for power. The relationship between current, voltage, and power that is absorbed by a capacitor. Now, a couple of things that we have to keep in mind. We've been talking primarily about ideal capacitive elements. Real capacitors have a voltage rating, and we have to be careful not to exceed this potential because it might provide sufficient energy for charges or a current to pass through the dielectric material. This would create a short circuit and can damage the capacitor. In fact, spark plugs are a good example of a controlled discharge of a capacitor. They are two parallel plates that are separated by an air gap, and in your automobile, to ignite the fuel mixture, the fuel and air mixture, it's basically providing a large enough potential to cause a breakdown and cause enough current to pass through the air, which is the dielectric material, which ignites the fuel mixture. Also, real capacitors cannot maintain a potential difference between their terminals indefinitely. So all real capacitors have a leakage current that results in a slow dissipation of the stored energy. This is because there's no perfect insulating material that will not permit any current to pass from the high side parallel plate to the low side or the negatively charged parallel plate. So over time, current will leak through the dielectric material and cause that electric field to slowly dissipate. Okay, and the next thing we're going to look at are inductors.